All right, so we're going to be talking a lot about collisions when we do linear momentum. And so there are actually going to be two kinds of collisions that we divide our types of collisions into, and these are going to be called elastic and inelastic. So the first one is going to be, like I said, elastic collision. And what this is that both momentum and mechanical energy are conserved during a collision. So both mechanical energy, which really, if we're on a short time scale right before and right after our collision, then really it's just the kinetic energy. So both mechanical energy, and I'll put there, it's the kinetic energy, and momentum are conserved in the collision. So this is going to be basically what happens when there's no delta U internal, right? So there's no internal energy created during this collision. Now, on a large scale, this is very rare because you get, some energy loss, some kinetic energy or mechanical energy loss from just sound or heating things up slightly. So on a large scale, it would basically say that this would make no sound. And if you have like magnetic repulsion between two carts, that's one way to kind of mimic an elastic collision on a large scale. But on the microscopic scale, you actually have quite a bit of elastic collisions on kind of like a scattering perspective of like, electrons scattering, and there's sort of field repulsions there at play. So it is an important part. However, we can never assume that it's elastic. So never assume that it's elastic. You must be told in the problem it's an elastic collision. And if you're not told, then don't assume. And otherwise, then we would have what's called an inelastic collision. And an inelastic collision is that only the total momentum is conserved. So total energy is always conserved, right? If we count up delta U internal and this lost energy. But when we talk about mechanical energy conservation, that's not conserved in an inelastic collision. So that means that there's going to be some delta U internal created. There'll be some sound, there'll be some heating, there'll be some, damage or smushing to the materials of basically just this additional energy that was taken away from your mechanical energy and added to the system. Okay, so that's going to be the main type of energy. The main type of collision we experience is going to be inelastic. So we need to be very careful not to use energy when we should be using momentum, right? So energy is specifically not the tool to use during a collision because of that added delta U internal. We don't know how much it is. So a couple common notes. One is in terms of problem recognition. When we do these combined concepts, one thing that you're going to notice is that momentum is going to be one of the easier ones sometimes, because what you're going to see is that anytime you have a collision, two things interacting, three things interacting, or an explosion, like I said, a firework, then you're going to use conservation of linear momentum. So if you have a collision or an explosion, then you apply conservation of momentum. And when we get to rotation, we'll also have conservation of angular momentum. So we'll see how those kind of can work in parallel depending on what sort of information you want about your collision. And then the other thing is that note that inelastic collisions can still bounce off of each other. Two things can hit each other and bounce off and still have turned some of that kinetic energy to internal energy. There still could be sound, there still could be heating, right? So just because they bounce off each other doesn't mean that it's elastic. So objects can bounce off each other in inelastic collisions. So If they stick together, we call that perfectly inelastic. And in that case, the most energy will have been converted to delta U internal. But they're all inelastic collisions. There's some delta U internal, whether or not they bounce off. You have to specifically be told that it's an elastic collision. Okay, let me know if you have any questions.